In this talking slide, we explore how to characterize the phase space of a linear system when complex eigenvalues are encountered. So what I will do first is have a look at the general theory and then give two examples. Complex eigenvalues occur when the trace squared minus 4 delta is less than 0. In other words, when we write out our solution to the characteristic equation, or quadratic solution to the characteristic equation, the thing in the square root, if that goes negative. Okay, so here's the solution to the quadratic equation or the characteristic equation. We have our two eigenvalues. If this thing under the square root is negative, what we then get is a set of complex eigenvalues. And even though the eigenvalues are complex, it's still possible to get a real solution to our linear system of equations. Okay, and so it's typically a trace part plus minus the complex part, where omega characterizes the complex part, namely it's then the square root of the positive version of delta minus tau over 4 squared. Okay, what results basically is a set of complex conjugate eigenvalues. In other words, they differ simply. The one eigenvalue cannot be obtained from the other one simply by taking the complex conjugate, and the corresponding eigenvectors are also complex. And part of the technical details of dealing with complex eigenvalues is how you combine these to once again form a real solution. Because remember, we're solving a real linear differential equation, and therefore the solutions we get only make sense if they are real, and therefore we have to make that clear in any answer we write down. Okay, so let's explicitly write out our complex eigenvector. It's simply C equals to A1 plus I B1, where A and B are real numbers. And the second component you can write out in a similar way. And then our general solution, we can actually use exactly the same theory as what we used when we had real eigenvalues, just elevating everything in terms of complex numbers. So what we have here is our constant term is now a complex number. In other words, C has component C1 plus IC2. This is now once again the exponent of the complex eigenvalue times T times the associated complex vector or eigenvector, and then we add exactly the complex conjugate term. In other words, we have another constant, complex constant e to the tau over 2 minus I omega t times the complex conjugate eigenvector. Okay, so there, just to make clear that C is now a complex constant, and what we're going to do now is we want to write the answer in terms of initial conditions. Once again, we have to ensure that we get a real answer, and there's an elegant way of doing this. So at times t equals to 0, we simply do what we've done in the past. We substitute the fact that t equals to 0 in there and in there, and then we get a solution for c's in terms of the x's. So let's do that. If t equals to 0, x of 0 is 0, and what we then get is that x0 is simply equals to c times the eigenvector plus the complex conjugate of that. And we can make an additional statement is, if we look at the time derivative of x at times t equals to 0, we can write that as a times x0 simply from the differential equation. And we can physically compute the time derivative of the solution we obtained, and that's simply the constant times the time derivative of the exponent, okay, evaluated at t0, so it's times c, plus the complex conjugate constant times the coefficient of the exponent of the eigenvalue times the complex conjugate eigenvector. So we now have two equations, or two vector equations. X0 is equals to cxc plus c star xc star, and we have that ax0 is equals to this combination, or simplifying it further, we have that ax0 is simply equals to half the trace times x0 plus I omega times the constant times the eigenvector minus the constant's conjugate times the eigenvector's conjugate. And the reason I have grouped it this way is that in what follows, we'll actually see that it is very, very useful when we want to write the solution, not in terms of the complex eigenvectors, but rather if we want to write down a real solution. Okay, so one more thing to recall that we're going to need to write down the real solution is that e to the I omega t is simply cos omega t plus I sine omega t. Okay, and then if we make use of these things, we can now massage our general solution to something that is actually makes it clear that it is in fact a real solution. So what we do is we write this first term as the constant times this complex exponential where we've actually factored out e to the tau over 2, the real part, times t in front, and the imaginary part e to the I omega t we are writing as cos omega t plus I sine omega t times the eigenvector. And we can do exactly the same for the second term. And what we get there, once again, we take out the real part of the exponential, we times it by the complex constant c star, and then the imaginary part we expand in terms of its real and imaginary components, times c star. Okay, the next step now is to group all the terms that come in front of omega t and in front of sine t. In other words, so we're going to write cos omega t times e to the tau over 2t times the constant times the eigenvector plus every coefficient of this. So we're going to plus basically c star e to the tau over 2t times c star. Okay, so there's what we get in front of cos omega t, and we do a similar thing and we group whatever is in front of sine omega t in the following way. And the great thing is we now have a real time dependence over here multiplied by a vector multiplied by the constants, with the constants involved. And in fact, we're fortunate that this combination is exactly determined by our initial condition x0. Okay, which is very convenient in that we can simply replace this combination by x0. And in a similar way, the second combination is once again appeared of something we can derive from initial conditions, namely it's exactly what appears over there. So you can basically subtract tau over 2x0 from ax0, and then the imaginary factor cancels and you just divide it by omega. So what we're now going to do for the next step is we replace these by the initial condition over there and in fact by its equivalent over here also in terms of the initial condition. Okay, and what we obtain as a result is a general expression for the solution if we had complex eigenvalues, and it's a real expression. So if we simplify this after we've made these substitutions from the initial conditions, our solution, if we have complex eigenvalues, is simply e to the tau over 2, trace over 2 times t, times cos of omega t times x0 plus sine of omega t times a vector we construct by dividing the matrix A by omega, subtracting the trace divided by 2 omega times the identity matrix multiplied in by x0. So both this gray x0 as well as this combination of stuff are vector quantities, and all the rest are scalars that explicitly give the time dependence. And so we can see the moment we have complex eigenvalues, we actually have an oscillatory solution. In other words, cos omega t, sine omega t, and the solution oscillates with a frequency equals to omega, which we compute simply by taking the square root of the determinant minus the trace squared over 4. Okay, very, very useful formula. Know how to derive it. When you do examples, you can either just simply use it, or you can in fact go through the whole complex use the complex eigenvalues and go through all these details I've just done in the derivation, as long as you ensure that at the end, the final answer, you actually write it in terms of real constants. So let's now look at two examples. The first being, consider the following linear system. X dot equals to minus 2x plus 5y and y dot equals to minus x plus 2y. You proceed just as we've done for all the other linear systems. Simply we have A, write down our matrix A, we work out the determinants, so delta equals to 1, we work out the trace, so that's 0. Okay, and what you immediately see there is you write down the characteristic equation, and its solutions has to have complex eigenvalues. In fact, the solutions are simply lambda equals to I and lambda equals to minus I. We then go ahead and work out the complex eigenvectors simply by subtracting lambda times the identity matrix from A and making sure we're in the null space of that complex matrix. And so we get C equals to 2 minus I and 1, and C star is simply its complex conjugate. We then go ahead and write down our general solution. So in this case, I'm simply using the method that is exactly the same as the linear method we used for real eigenvalues, so that you see how it works directly. And so here we have x of t equals to a complex constant, and you must remember it is a complex constant, e to the I omega t x c plus c star e to the, I'm missing a minus sign over here, minus I omega t x c star. Okay, so there's a typo. And so, which fortunately got fixed in the next slide. So here we have the solution written out. Okay, remembering that these C's are complex constants, and we can now go ahead and simplify it a bit. And in particular, we're now going to simplify it further. We're going to fix the initial condition, use the initial condition to fix what the complex constant is. And the way we do that is we say at times t equals to 0, the vector we're looking at is simply, okay, 2c plus c star minus I c star minus c. So that's just the first entry. Plus the lower one is simply c plus c star, and you can see I must actually take the transpose of this, so I just wrote it all in one line for convenience. Okay, and that immediately gives us that if we write out the fact that c is a complex number, in other words c1 plus I c2, if we simply substitute that in there, we get that x0 is equals to 4c1 plus 2c2, and y0 equals to 2c1. Okay, and then we solve that, and we get c1 equals to y0 over 2. Substituted in the second expression, we get c2 equals to x0 minus 2y0 over 2. And that then permits us to put that back into our general expression and simply find a general solution for x and y in terms of t. And we see that it is simply x0 cos t, y0 cos t, plus this linear combination of x0 and y0 times sine t. And if you were to go back and compare this to the formula we derived on the previous slide, you'll see it's exactly the same. So when you get a practical problem, you can either use the formula that we derived, the real formula, or, which I often do, is I simply go through the things, simply elevating the eigenvectors and eigenvalues to being complex numbers, and then plug through the whole thing, simply finally substituting my initial conditions and making sure that the final result is in fact a real solution. Now let's have a look at the phase plane. So this has got a very interesting phase portrait. In fact, you can already see that it's an oscillating function because you have a cos omega t dependence, and let's see what it does. So the method for drawing the phase plane or the phase portrait is very, very similar to what we've been doing for the real complex eigenvalues. You first put in the null lines, in other words, x dot is equals to 0 when y is equals to 2 over 5x. You work out the arrows on it. If x is positive here, the arrows point down. If x is negative, the arrows point up. And you work out the second null line. It's simply y dot is equals to 0 when y is equals to x over 2. And there you know the arrows point either left or right. So we put it in. So over here you see the arrows are pointing to the right. Here they're pointing to the left. And you can see therefore that the trajectories at least here are going to go across there, and then they've got to bend round and go up. So you're going to have little curves like that happening over here. When I have complex eigenvalues, I always plot my vector field on the x and the y axes, because you'll see you will not be able to plot the complex eigenvalues. They don't have a direct meaning in your plot, but you will need more information than just the null lines to actually plot the trajectories themselves. So in the case of complex eigenvalues, I always put the vector field on the x-axis. I simply substitute x equals to 0 in here, and then draw the arrows of, I simply substitute, y equals to 0 in here, and then draw the arrows according to what x dot and y dot is. So here you can see if x is bigger than 0, x dot is negative, and y dot is negative, so our arrows point like that towards the third quadrant. If x is less than 0, you're going to have that y dot is positive, the arrows point up, and x dot is also positive, so they are pointing in that direction towards the first quadrant. Okay, do the same thing for the y-axis, namely when x is 0, I substitute the value in here and evaluate what x dot and y dot are, and you can see then plot them and draw the arrows like that. And so this now is enough information. You're going to have something that tends to go round, make a little loop over there, and then go back. Okay, and the oscillatory nature, you can actually see that by the fact that the size of the vector, it completes a complete circle after basically t equals to 2 pi and gets back exactly to where it started. So in the case where you have complex eigenvalues and zero trace, you're always going to get closed ellipses or closed circles. And just to give you a feel, here is the complete vector field just put in, so you can see the things or the trajectories basically want to do something like that. Okay, and then we can plot them. Specifically, we can plot the solution. You can either just draw it by hand or substitute x0 equals to 2, y0 equals to 1 into this expression, and you're getting your closed curves. You can plot some other trajectories, and you can plot some other trajectories like that, and they will always be closed ellipses. Right, so if we have now the special case, if tau equals 0 and the determinant is positive, then every trajectory is closed, and what we're dealing with is basically a center. Okay, so this is one example of a system that has complex eigenvalues. You basically can follow exactly the same method as what you did for real eigenvalues, just at the end ensuring that you actually get a real answer by substituting in the initial conditions to find the components or the real imaginary components of your constants that you are using to describe the real solution. Let's now have a look at the next example. Okay, let's consider this linear system. X dot equals to minus 3 over 4x minus 2y, y dot equals to x plus 5 over 4y. We once again write down our matrix A, and we work out the determinant, and we work out the trace. And then this is not entirely obvious that it's a complex eigensystem, but we simply go and then work out what this combination that appears in the square root is, namely tau squared minus 4 delta. We find that it is minus 4, and then we immediately know we're going to have complex eigenvalues. Okay? And in fact, what we are going to get is an unstable spiral. Okay? It's unstable because the determinant is positive. Okay, so both eigenvalues have the same sign, and the trace is positive. Therefore, the eigenvalues themselves are positive, so they're unstable. The real part of the eigenvalues are positive. The solution will tend to move away from the origin. And And our characteristic equation is simply lambda squared minus half lambda plus 17 over 16, which has eigenvalues that are complex. So lambda is equals to a quarter plus I, and lambda star equals to a quarter minus I. And then we can once again work out the eigenvectors associated with lambda, and there they are, also complex eigenvectors. And then we can go ahead, and in this case I'm simply going to use the general solution we derived rather than go through the whole linear process that I did in the previous example. But you can see here in the general solution that it will be an unstable spiral, because here as time grows, the norm or the size of the solution will grow exponentially with a rate of t over 4, or with a rate of t over 4. Okay, and then you have cos of t multiplying the initial position, and you have sine of t given with a vector that is simply a minus 1 over 4i times the initial condition. Okay, and if you write it out in component form, here is what a minus a 4i times x0 is, simply written out. Okay, so now let's look what the phase plane looks like. Once again, the technique of plotting it is 1, plot the null lines where x dot is 0. You have that y equals to 3 over 8 minus 3 over 8x, where y dot is 0, and you can put in the arrows simply by picking points or 1 or 2 points on the line. So it points up if x is positive, down if x is negative. The second null line is when y dot is equals to 0. There we have the line y equals to minus 4 over 5x. And once again, we can put the arrows left if x is negative, right if x is positive. And you can so see that the spiral is going to tend to go across this line to the right and then up across the second null line and tend to make a circle like that. To get an even better picture, remember unstable, complex eigenvalues, I always plot the vector field on the x and y axes. So here we have when y is equals to 0 and x is positive, the arrows point in that direction. If y is equals to 0 and x is negative, the arrows you can plot point in the other direction. Same thing is true for the y-axis. When x is 0, you can also simply evaluate x dot and y dot when x is 0 over there, and then put in the arrows on the y-axis. And so now you have a very good idea of the nature of motion of the spiral. You also know that the norm of the spiral is going to grow exponentially. And so if you plot it and view the full vector field, you're going to get something that looks like this. Okay, it's basically if tau is greater than 0 and your determinant is greater than 0, every trajectory spirals out to infinity. You have and this is something that they call an unstable spiral. Okay. In a similar fashion, if your trace was negative over here and your determinant was positive, you would simply reverse the arrows and you would have a stable spiral. So the trace, in the case of negative eigenvalues, imaginary eigenvalues, determines whether your spiral is stable or unstable. Okay, so this basically concludes our lecture on complex eigenvalues, and I hope it has been useful. Thank you very much.